Okay, so now we're going to start talking about engines. And this is where the thermo class kind of deviates, applied versus like a normal thermo class, because normally you would go second law, and then you go over, talked about Exergy, but we're kind of just going to go to engines because that's one of our applications, right? This would be like the automotive application. And so we're kind of just going to go ahead and skip over Exergy and move on to engines. So yeah, let's go ahead. Just kidding, we're talking about Exergy. Okay, so the idea with Exergy is it's called the work potential. So the idea is that I have a system right here, like let's say I found an oil well or something and I want to know how much useful work, how much useful energy can I get out of this, right? And the idea is that I'm going to be able to extract the most useful energy by taking this system in a reversible process from its state to what's called the dead state, which is basically just the state of the surroundings or the area around it. Because the idea is that even though something like the atmosphere might have energy, I can't really extract that because it's already at the state of the surroundings, right? I would have to change the energy, which would require moving it to a different location or somewhere, pumping in energy or out, if that makes sense. So you can only really extract energy if you're changing the state. And if you want to be able to do that in an efficient way, you can't add as much energy as you're taking out. Otherwise, you're not getting a net output. So basically what we're going to do is we're just going to do a quick like energy balance, right? We've done this quite a lot before. So basically a small amount of heat output and work output has to equal the change in energy of our system. We would have internal energy, kinetic, and potential. I'm going to just call all this E real quick just so it's a bit easier to write this out. Now, the ways that we can extract work from our system are one, we can do the boundary work if we're talking about a reversible process, right? So if we have like our piston cylinder and it moves out some, we're going to be able to extract useful work from this P delta V, like we talked about before. But the problem is we also do work on the surroundings, right? So since we want to talk about the total work that we could get out of this thing, we don't just want to look at the system anymore. We also have to consider, because the kind of surroundings were right here, and now they're up here. So basically the amount of work that we can get from the boundary that's useful, I guess we could just talk about all the boundary work. So this would be B equals the amount of useful, which is what we actually want to be able to work with, plus the amount of work that's done on this outside kind of surrounding system, which would be P naught. This naught notation is what's called the dead state or the surroundings. So the pressure of the surroundings times the change in volume would give us how much work is being done to the surroundings. Now the other thing we can do is we could extract this heat transfer. And the way we would do that is with a heat engine like we've seen before. So the work from our heat engine is going to equal the Carnot efficiency, which is our 1 minus T low, which would be our environmental over the temperature of our system, times the amount of heat we're adding, a small slice of Q. So this would equal like a delta Q minus a T naught over T if we just distribute this. And now if we take this delta Q over T and we use our entropy definition, this would give us a minus T naught ds. Just so it's clear, this is a capital S. I'm going to underline it. Okay, now if we solve for our delta Q would just be the work from the heat engine minus our T naught ds. And the reason is because this is a heat transfer from the system. So this is actually going to contribute to negative. So I know we have a negative sign right here, but this is minus the output. So this would technically be a minus negative right here, because when we have heat leaving the system, we're going to decrease the entropy. So we would add this over and it would stay as a negative. Okay, so now what we can do is we could plug this in, our total work output and our total heat output, into this equation right here. And what we would get is that we would have, well, let's just plug it in, right? We'd have our delta work useful plus our P naught dV plus the work from the heat engine minus our T naught ds has to equal our dE total. And now if we just want the useful work that we can extract, it's going to be from the heat engine and from this useful boundary work. And then real quick, because we have the negative signs on both of these, I'm just going to move them to the other side. So we'll go ahead and plop in a negative sign right here. All right, and now we can say that the exergy, which is the total useful work that we can grab from the system, is going to be the useful boundary and the heat engine work. So we can just go ahead and add this over and subtract this over. So this negative dE, I'm going to break it into its constituent components. The first we would have is we'd have our delta U. So normally we would say our final minus our initial, but because it's negative, we'll do our initial minus our final, which is the dead state energy. Then we'll add this P naught times our final minus our initial. So although we would subtract it over and get a negative, since I'm switching it to final minus initial, it's going to go positive. Same thing with our T naught delta S, or our DS. And then we're going to have, I guess I should break open this DS because that's our change, right? We'll have our S minus S naught. So the idea here is that I'm basically adding and subtracting over the differentials, and then I'm integrating from my final to my initial state. And then I'll also have to consider our changes in energy. So we'd have mv squared over 2 plus an mgz. Okay? And the reason that we're doing it this way is this is basically the V relative to the surroundings. Everything when we talk about exergy is usually relative to the surroundings because the whole idea is that you can only go up to the surroundings. So normally I would have an M times a V squared final minus a V squared initial all over 2, right? But we're saying that the initial, or I guess the final right here, is going to be 0. And then because I have a negative dE, this negative sign is going to cancel out. And it's the same thing for our potential energy. Normally we would have an mg delta z, but instead we're just going to write it like this. Now you could also have exergy in terms of mass flow, right? So we're going to eventually do an exergy balance equation. And that would basically, you just need to include your enthalpy. So normally how this is written is you would combine them. You would say that your exergy from the flow is, you would basically combine this U and this PV. So you would have H minus H naught plus T naught. This is all in terms of specifics. So this is S minus S naught plus, and then we'll have V squared over 2 plus GZ. So this is basically the specific energy that you have for some amount of mass. And now we can talk about the open and closed exergy flow really quick. So for a closed system, our change in exergy is going to come from, first we'll have heat transfers. So basically how much useful energy can we get from the heat transfer? Well, it'll be the Carnot efficiency, which is our 1 minus T naught over T of basically wherever the transfer is happening. So the T naught is our external, and then Tk is the boundary temperature. We're summing over K times Q K. So K is basically just our subscript as we're adding things up. And just real quick to remember that this right here is the efficiency of basically work output we can get divided by Q in. So if we multiply it by Q in, this is the total work output we can get. We did the same thing earlier. And then we'll have to subtract the amount of work done by the system. That's our convention. So W is basically the useful boundary work, and then minus, our P naught times our V2 minus V1. This is the work that's done to the surroundings that we can't extract usefully. And then we'll also have something called exergy destruction, which comes from entropy generation. Basically, when we generate entropy, there's some energy that we lose that we can't extract as useful anymore. And if you basically look at an isolated system with no energy transfer whatsoever, it can only generate entropy, right? Which means that it can only destroy exergy. And if you go ahead and you simplify out that equation, you'll get that the exergy destruction is equal to our environmental temperature times the amount of generated entropy, which makes sense because this is an energy unit. This would usually be something we look at like heat transfer. And so that's for the closed system. For the open system, we also got to worry about mass transfer. So we're going to first have the, I guess we should write this in rate form. So we'll have our delta x. No, there's no dot on here because we already have our derivative with respect to time. This is going to equal adding up all of the heat transfer rates. So we'll just do a T naught over TK. TK times our QK. K, this is a rate form, so we put a dot over it. Then we'll have to subtract our W dot minus our P naught times basically our dV dt. Because we're looking at a rate form now, we can't just have a final and initial. So we'll write it like this. And we'll also have to examine the surroundings. So we'll have to add up all of the mass flow rates in, so our m dot in times the exergy of that flow minus adding up all of the m dots out times the exergy of our outflow. And then lastly, we'll have to subtract the rate of exergy destruction. And so now we can get back onto the main quest. We're going to start talking about engines, and our model for an engine is the gas power cycle. So basically, we're going to assume, I guess I should just talk about all these assumptions because we have quite a few. First of all, we're going to idealize it as a reversible process. All of the components of our process are irreversible. We're going to ignore any like complex real behavior. Our first assumptions are going to be first, like no friction or pressure leakage or anything like that, anything that would create irreversibilities or something more complicated to look at. All expansion is quasi-equilibrium, which basically means that it expands slowly enough that it's infinitesimally close to equilibrium at all times, which means that you're going to have a uniform mixture as it expands or compresses. And lastly, we're going to assume that the heat transfer, or basically the heat loss, is negligible. We are going to have to model combustion, which is going to be modeled as a heat input basically. But aside from that, when we're just talking about the expansion or the compression, we're going to assume that there's no heat transfer. Then we also have the cold air assumptions. So we assume that our working fluid is air. In reality, be a combination of air and our fuel, like, unleaded gasoline or something. Air is an ideal gas, and we're going to assume that it circulates in a closed loop. So basically, we go through a full cycle. All processes are internally reversible. We already talked about that. Right here, combustion and exhaust are replaced by heat addition and rejection at constant pressure is also our assumption there. And then lastly, 4 is constant specific heats with respect to temperature, so we don't have to worry about integrating our CP delta T. So we're going to look at two engines in this, but they're both going to have very similar properties. They're all going to look like this, basically. So if you actually look at an engine, this is what a cylinder of an engine looks like. You can see right here, this is our cylinder, and it goes up and down. This right here, this orange thing, is our piston. So basically the way the engine works is it goes bonk, 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 up and down, right? And that generates the work output that we want. This right here, the lowest it can go is called bottom dead center. The highest it can go is called top dead center. This is just some vocabulary you're going to need to know. When it's at the top, there's still some volume that it has. This is called the clearance volume, VC. And the volume that it basically takes up as it moves from top dead center to bottom dead center is called the displacement volume right here. You can also get it from something called bore and stroke. So stroke is how much it goes up and down, and bore is the diameter of this cylinder. The way the engine works, we also have intake, which is where the fuel goes in, exhaust, which is where the fuel goes out. If we're talking about a spark ignition, which is the first one we're going to look at, we'll have a spark plug right here that's going to basically use the spark gap to ignite and start the combustion. So that's the basic of how the cylinder is going to work. A couple things that they're all going to have in common is the compression ratio first, which is basically equal to the ratio of our maximum volume, so our volume bottom dead center divided by our volume at the top dead center. And another thing they're all going to look at is the mean effective pressure, which is basically the pressure at which it would be equal if we just did like a constant pressure work output. So if you remember, our work output is like integral of PdV. So if we take our work output and we divide it by essentially our volume right here, so our work output net divided by our displacement volume would be the effective pressure, basically the average pressure that it would work at in order to get the same work output. So that's the basics of our engine, right? You could also do some more calculations here. So like if you want to get the displacement volume from these guys right here, you would just do like our VD is pi over 4 times our diameter squared times our height, right? Or you could do our clearance volume. There's a lot of equations. I think it'd be more useful for you to just think about this diagram right here and what you can get out of it. But right, this would be what, like our V BDC minus TDC and things of that nature. So this is all actually real stuff that you might see in like an engine. Like you can go find the bore and the stroke for engines. Like this is normal like industry terminology. And basically the way the engine is going to work in terms of just like effectively, we're going to look at something called two-stroke, usually for idealization, which basically just means that we have expansion compression, ignition, and exhaust. But normal engines usually work on a 4-stroke cycle, which is this is the PV diagram for it. Basically, the way it works is we're going to start by filling the cylinder with fuel. This is going to increase the volume, but not really give us much pressure until stage 2 when we close off the intake, and then we're going to start compressing it, and then it's going to compress more and more and more. The pressure is going to increase, the volume is going to decrease until 3. This is where combustion starts, so either auto ignition if you're talking about diesel, or that spark plug ignites it. Boom, big increase in pressure, and then the cylinder is going to start going down. It's going to get more and more and more in volume until right here, which is when we open up the exhaust and it starts closing off here, and then we're back to state 1. And this would basically be where a piston would be. So bottom dead center is right here where you have the most volume, and then TDC would be right here. So let's go ahead and look at our first one. The Otto cycle is a spark ignition, like I just talked about. So basically what we're going to have, if we look, these two diagrams will be pretty useful. The way that the 4-stroke would work is basically you would start here, right? You go here, up, down, and around. This would be our idealization of it. So we're assuming that the compression and the expansion are isentropic, which means constant entropy. And then also we're assuming that because the exhaust and the combustion happen so quickly, that we're assuming it's constant volume. And now if we were to do the whole 4-stroke cycle, we would go to state 0 right here, which is what I have labeled. But the work output and the work input between these two would cancel out. And so usually we don't bother looking at that. We're just looking at this cycle right here. So if you want to talk about some of the quantities you can get, the first one you might want to look at is Q in. So when we're getting Q in is basically during our combustion process, right? So right here from 2 to 3. So if you imagine we'd have our internal energy at state 3 minus 2, which would be the same thing as our CV if we're assuming our constant specific heats, times T3 minus T2. Same thing for Q out, except now we're looking between states 4 and 1, so we'll have our U4 minus our U1. It's constant volume, which means that we can do our CV delta T again, just like that. Okay. Now, if we want to get our thermal efficiency, we would just need our net work divided by the heat input, right? And so this would be equal to Q in minus Q out, right? Because that's the only way we can get energy into or out of the cylinder is basically heat input, heat output, or work in or out, because our model is a closed system, even though in reality we would have combustion and exhaust, and we would have the intake and the outtake. All of this would be divided by Q in, which we simplify, this would be a 1 minus Q out over Q in, right? Now notice that if we plug in these guys right here, our CVs are going to cancel in this fraction, and so we're just going to be able to rewrite this as equal to a 1 minus our Q in, or I guess our Q out's on top, so we'll just do a T4 minus T1 over T3 minus T2. And now we're going to rewrite this once again, just because it's going to be a little bit easier to get it into the form that's going to be easiest to work with, is we're going to pull out a T1 from the top and a T2 from the bottom. So I'll have a 1 minus T1 times T4 over T1 minus 1 over T2 times T3 over T2 minus 1. And the reason is because now they're all in terms of fractions. And the reason that we want that is because we're going to pull in those isentropic equations we talked about in the entropy episode. So if you remember, in the entropy episode, we had stuff like, we had like our T1 over T2 for isentropic. I also have the TS diagram right here, just so it's easier to see, because this says S equals constant, but the TS diagram would be vertical for S equals constant, and then we have the corresponding constant volume. So between 1 and 2 and 2 and 3, we have isentropic, which means we can use these isentropic relations. So our temperature ratio is the same thing as our volume ratio, so our V2 over V1 to the power of K minus 1. Since our working fluid is air, K is something that we're just going to know, and this has to equal our V3 over V4, because the ratios of our volume between 1 and 2 and 2 and 3 are the same, right? It just goes between top and bottom dead center. All of this to the power of K minus 1, which equals a T4 over T3. And now, one thing to remember is that remember that compression ratio thing I was talking about earlier, right? The bottom dead center over the top dead center. Well, that's going to come in handy here because it's usually something you're going to know. You can go look up the compression ratio for like a real engine, but it's going to equal basically V4. Usually we go 1, 2, 3, 4. So the way that you would write this, it's going to be a little bit easier with the volume diagram, is V1 over V2 or V4 over V3 are both valid ways of writing the V1 over V2 and V4 over V3. These are both valid ways of writing the compression ratio. So this right here or sorry, I wrote V1 there. This should be a V4. My bad, I miscopied it. The whole reason we want to do this is because this is equal to 1 over R, right? And this one right here is also equal to 1 over R. And so if you plug in these fractions into this, what you can do is you can simplify the thermal efficiency a lot so that it's literally just dependent on K and the compression ratio, which makes it a lot easier to find. So your thermal efficiency, if you're given R, this is definitely going to be the easiest one to do, is a 1 minus 1 over R to the power of K minus 1. And so this right here is basically how the Otto cycle works. We just assume constant volume, heat addition, and heat rejection for our exhaust and our combustion processes. You can find your Q in and your Q out and all those things. Constant kinetic and potential energy is also something that we technically assumed that we didn't really talk about because, well, the cylinder isn't usually, I mean, technically it could be accelerating, right? If it's in a car or something, but that's usually negligible compared to the big combustion you have in your engine that's actually producing work output and is kind of designed to do that. So now we're going to talk about the diesel cycle. So the way the diesel cycle works is it compresses a lot more. It has a much higher compression ratio. And basically, it's going to reach auto ignition, which means that it's just going to start combusting all on its own, which means that our constant volume heat addition is no longer like an accurate model. Instead, we're going to talk about constant pressure heat addition. Because we're no longer at constant volume, we're also going to have work done from our PDV. So if we think about our Q in right here, this is going to be Q in, and this is right here is going to be Q out. Because this is our TS diagram, I guess I should shift over a little bit so you can see that that's our TS diagram, right? So the idea is that the area under this is going to be the heat output. So if it's positive, if we're going to the right, then we're having heat input. And if we're going to the left, then we have heat output. Okay, so our Q in is going to equal 3 minus 2. So we're going to have our U3 minus U2. And then we're also going to have to do our P delta V though. So I guess a better way to write this is we're going to have both heat and work when we're talking about this. So our Q in minus our work output equals U3 minus U2, right? That's just like our conservation of energy minus the kinetic and potentials. But this W is just going to be our PDV, so we can find that our Q in, if we solve for it, it's going to equal our P2 times our V3. V3 minus V2 is constant pressure, so we could have done P3 here. P3 and P2 are equal, right? It doesn't really matter. V3 minus V2 plus a U3 minus U2. And now P2, right, P2, V3 are the same thing as P3, V3 minus P2, V2 is our enthalpy if we also combine it with this. So we go ahead and combine these and we get our H3 minus H2, which if we're talking about a gas is the same thing as our CP times our T3 minus T2. So boom, that right there, that's how we can get our Q in. Our Q out is going to be exactly the same as the Otto cycle. So I'll just go ahead and write it real quick. This is going to equal, right, our U4 minus U1. Technically, it would be final minus initial, which would be U1 minus U4. But then we get a negative for Q out. So if you just want the absolute value of the Q out, then you do U4 minus U1. And this is going to equal our CV, constant volume specific heat, times T4 minus T1. Right? And so now we can get our thermal efficiency. basically we would just do the same thing. We'd plug things in. So our thermal efficiency is our W net over Q in. We've seen this before, which equals Q in minus Q out over Q in, which equals 1 minus Q out over Q in, which equals, now if we go and plug in our Q out and Q ins that we solved for, we would have, so then we would just do a 1 minus Q out over Q in, which would be our Q out here is our CV, T4 minus T1, and then our Q in is our CP times our T3 minus T2. And now if we use the fact that K is defined as a ratio CP to CV, we can get rid of these and we can just put a 1 over K. And then we do the same thing where we'd pull out the T1 and the T4, and we'd use our isentropic equations. And if you do all that, what you would get is that the thermal efficiency in terms of our ratios is equal to 1 minus, this one's a lot more complicated, 1 over R to the K minus 1 times some stuff, RC to the K minus 1 all over, to the K quantity minus 1 all over K times RC minus 1. And you might be like, hey, what's this RC thing? And this is called the cutoff ratio. So the cutoff ratio for diesel is basically just the ratio of the volumes that are combustion. So it's V3 over V2. It just simplifies things a little bit so we can write our thermal efficiency in this nice little equation. So RC equals V3 over V2. And because this quantity right here is always greater than 1, if you go ahead and you simplify it, our thermal efficiency for the diesel cycle for the same compression ratio and the same R and RC basically is always going to be less than the diesel cycle. The diesel cycle is always going to be less efficient than the Otto cycle. But the reason that diesel's still useful is because we can get much higher compression ratios. So usually our thermal efficiency might actually even be higher. The reason is because the Otto cycle right here, our spark ignition engine, if you compress it too much, if you give it too much of a compression ratio to the point where it reaches auto ignition, then it's going to create the thing we talked about earlier, engine knock, which usually leads to kind of a violent reaction, which is not good for the engine and also doesn't produce a lot of work output. So yeah, that's kind of why the diesel engine is useful. And this right here would be a kind of model of a combined one, which would probably be a bit more realistic. So you can see right here, we've got our compression stage, then we've got a constant volume heat addition and a constant pressure heat addition. Then we reject it, exhaust, and then we have a constant volume heat rejection. So yeah, that's it for engines. Next time we're going to talk about power plants.